Here we are in 10.5, the last section in chapter 10 for us. We're going to solve exponential and logarithmic equations. So you can see I have properties 2 and 3 from the previous section. They are going to be invaluable here in solving equations. So we've got the log of b raised to the x with base b. Those two bases, if they're the same number, they cancel out, and we just get x. Same thing if we switch up the order. Base b, the log of x with base b, those two base b's cancel out, and we would have simply x. So let's go for it. We're going to solve starting with this. So at first it seems familiar. 3 raised to the x plus 5 equals 8. We saw equations similar to that way back when we first introduced exponentials in 10.2. But here's the thing, back then this number over here could be rewritten with that base 3, right? We could write that as 3 raised to the something. Well, it's not the case here. So we've got a more general way to approach this that will work for any number that we see, whether we can rewrite it with that same base or not. Here's what we're going to do. Here's the question. To cancel this 3, we want the inverse of the exponential with base 3, right? That's an exponential with base 3. Well, what is the inverse of an exponential with base 3? It's a logarithm with the same base 3. We are going to take the log with base 3 of both sides, and you're going to see that first property that we wrote up above in play, in action. Okay, so to take the log with base 3 of both sides, here's what it looks like. The log of base 3 to my left, log base 3 of 3 raised to the x plus 5. If I do that to the left, I need to do it to the right. So we've got the log base 3 of 8. Now what good does that do? Because these are both base 3, these cancel out. And all we're left with over here is that x plus 5. All right, that base and that base cancel. This thing simplifies to whatever that exponent was. In this case, x plus 5. And just like that, we're really close to the answer. All we need to do to get x is subtract that 5. So here, x equals the log of 8 with base 3, whatever that number is, minus 5. We're going to call this our exact answer. Now, oftentimes, it's useful to have the exact answer, but sometimes we like a rounded answer also. So here's what I'm going to do. To get the decimal version of that answer, I'm going to use the change of base formula here on the log of 8 with base 3. I kind of like those natural logs. So I'm going to say this is the natural log of 8 divided by the natural log of 3, right? Change of base formula applied to this. And I'll subtract 5 on the end. So I'm just going to put this in a calculator. And that's the answer right there. Negative 3.1072. I went to 4 decimal places. So there's my rounded version. Pros and cons, strengths and weaknesses. So it's not unusual for questions to ask for both the exact and the rounded versions of your answer. Okay, so of course the key was, way back here at the beginning, recognizing we had an exponential with base 3. So to cancel that out, we needed a log with base 3. And then it was pretty quick after that. All right, let's try another one. Here's another exponential equation. Okay. 7 plus 3 e to the 5t equals 13. So the first thing we want to do as we're looking at all that is to isolate our exponential. We need to get that by itself. We've definitely seen this theme of isolating, right? When we were solving square root equations, we had to isolate the radical before we could maybe square both sides, that sort of thing. We definitely we've seen this first goal in solving equations quite a bit. So how are we going to isolate that e? Well, we're going to subtract the 7, start there. We're going to divide both sides by 3, and there we have it. We even need to get that 3 out of there. We don't want that. We just want the exponential only. So we've got a base e and its exponent, and then it equals one number. Okay. At this point, we find ourselves in the same situation that we were at in the last problem at the very beginning. We've got an exponential with a base. There's no way we can rewrite the other side with that same base. So what are we going to do? Well, we're going to think, all right, I've got an exponential with base e. So I need to take the log of both sides with that same base. Hey, what is the log with base e again? The natural log. We are going to take the natural log of both sides. So here it is. The natural log of e to the 5t equals the natural log of 2. And of course, what happens? The natural log of e, we've seen this in a few examples, even leading up to this section. The natural log of e cancel out, right? Natural log has base e, so it's that same property coming in here, and all that's left is 5t. 5t equals the natural log of 2. All right. All we got to do is divide by 5, and we will have the exact version of our answer. The natural log of 2 over 5. Now if we want the rounded version, well, it turns out we don't need change a base formula here. We've already got a natural log there, so I can just grab my calculator, natural log of 2, whatever that is, divided by 5. And this is the rounded version, 0.1386. Okay, so of course the key step, right, we had to, well, I guess a couple things. We had to recognize we needed to isolate that e, and then to cancel out the e, we take the natural log. E and natural log are opposites, inverses. And then we're just a couple of quick steps away. Of course, if you ever wanted to, you could take your rounded answer, plug it back in to the original equation, see if that works out. Okay, so I've got one more before we stop this first video. The log of 2x minus 1 base 6 equals 4. Now we're switching things up. Now we've got a logarithmic equation. The previous two examples were exponential equations. So what's the difference? What's going to happen here? Well, turns out it's the other property. You remember this one? The second property that we put up. If we've got a logarithm, then we're going to cancel it by putting it in the power of the same base. So let's think about this. I've got a log with base 6. So what we're going to do is put both, it's kind of strange the way it's worded, but it is what it is. We're going to put both sides in the power of 6. Now this is a really bizarre thing to do to both sides of an equation, but I think we'd all agree it would have to logically follow, since we're doing the same thing to both sides. We're going to put the left side there up in the power of 6. And we do the same to the right. We put that 4 up in the power of 6. So 6 raised to the log of 2x minus 1 with base 6 equals 6 raised to the 4. Okay, I guess you could do that to both sides if you really wanted to. Yeah, as long as you do the same thing, it's got to be true. Why? Because this exponential base 6 and this log base 6 cancel out. And just like our property says, it's going to equal that exponent. So the next line, 2x minus 1 is equal to, and here I'm just going to go ahead and multiply that 6 to the 4th out. It turns out it's 1,296. And once we have that, well, we're pretty close to the answer, right? We can add the 1, divide by 2, and we got it. You might write this answer as 1,297 over 2 as the fraction. Maybe you prefer the decimal version. There's really no rounded here. They're both the exact version. We didn't have to round anything. 648.5 is an exact answer also. Okay, I've got one more example for us to do together. Turns out it's another logarithmic equation, but it's a bit lengthy, so we're going to save that for the next video.